Okay, so as I was saying, we're going to do 5.8 and 5.9 today. And both of those sections are dealing with inverse trig functions. And so in section 5.8, we're taking the derivative of inverse trig functions. So you probably remember, hopefully remember, on your calculators, if you do second sine, second cosine, second tangent, you'll see the little sign with the superscript of -1. That's on the 84. Those are the inverse trig functions that I'm referring to. So sine inverse, cosine inverse, and tangent inverse. Have you ever heard these trig functions referred to as arc sine, arc cosine, and arc tangent? Does that sound familiar at all? Okay, I see a couple of nods. So sine inverse and arc sine are exactly the same thing. It's just two different ways of writing it, but they mean exactly the same thing. So if I ask you to find the derivative of sine inverse, that means the same thing as if I ask you to find the derivative of arc sine. There is no difference. It's just two ways of expressing the same thing. Also, as Nick mentioned earlier, these functions are normally used to help us find angles. So probably when you worked with these functions, you may have been given an equation to solve, like, let's say I ask you sine of theta equals a half, and I want you to find theta. Then to get theta, what we have to do is take arc sine of both sides. So I would do sine inverse of this side, sine inverse of this side, and we get theta equals sine inverse of 1/2. And what that's asking me is where on the unit circle is sine equal to 1/2. So you're looking for an angle. You're solving for theta, so you're looking for an angle. So you just think about on the unit circle, you know, sine is the y value. So think about where on the unit circle is the y value equal to positive 1/2. What is it?
30 degrees.
Okay, give it to me in radians.
It'd be pi over 6.
Pi over 6. So that would be one place on the unit circle where sine is 1/2. Now remember, there's actually two places on the unit circle. The first trip around where sine is equal to 1/2, but in a problem like this, you're normally given a restriction, like find the angle between 0 and pi, or between 0 and 2 pi, or that sort of thing, so you can decide how many angles you actually have to list. Now, we're not so much doing this, we're just taking the derivative and the antiderivative of this function, but I felt like it was important for me to remind you what these functions do. This is where you have seen them before. What we're doing with it is really just learning formulas for finding the derivative and the antiderivative of these three inverse trig functions. So let's get started on the derivatives, which is 5.8. So we're going to do the derivative of arc sine of u, so d by dx of arc sine of u, and it's going to be u prime over the square root of 1 minus u squared. That's the formula for taking the derivative of arc sine of u with respect to x. Because remember, u can be any function of x. Then we're also going to need to find the derivative of arc cosine, or cosine inverse. and the derivative of arctangent, or tan inverse. Then the derivative for arc cosine is the same formula as the derivative for arc sine, except for it's negative. So it's going to be negative u prime over the square root of 1 minus u squared. And then for arctangent, you're going to have u prime over 1 plus u squared. Now, there are proofs out there as to why these formulas work and where they come from. And lots of times I'll show you those types of things. In this case, for now, you're just going to have to trust me. You're going to take my word for it. But just know that there are proofs out there if you're interested. You can look them up and kind of do some research outside of class. For us, what I want you to just know the formulas and be able to apply them. So let's do some examples. My first example is going to be find the derivative of arc sine of 2x. Find the derivative of arc sine of 2x. So in this case, my u is what? 2x. My u is 2x. So if I go to substitute into my formula, u prime is just 2, so that's going to go in the numerator of the fraction. So 2 over the square root of 1 minus, we just said u was 2x. Make sure you put that in parentheses and then square it, because not only do you have to square the x, but you also have to square the 2. That's important. So answer, 2 over the square root of 1 minus 4x squared. Bless you. That's it. Can I take the square root of 1 minus 4x squared?
No.
1's a perfect square. 4x squared is a perfect square. I cannot take the square root of 1 minus 4x squared because it's a binomial. Those are connected. So as tempting as it is, you can't take the square root of 1 minus 4x squared. Okay, let's look at another one. So my second example is going to be take the derivative of arc tangent of 3x. So in this case, my u is just 3x. So if you look at your formula, it's u prime over 1 plus u squared. U prime over 1 plus u squared. So u prime is just 3. And then 1 plus u squared. Remember to square both the 3 and the x. And you get 3 over 1 plus 9x squared. Now, I think that most of you will agree with me that this is not difficult as long as you know the formula, right? The hard part is you have so many formulas to memorize already, and now we're adding 3 more. That's the hard part, is just keeping all the different formulas straight, because on the AP exam, you don't get a formula sheet, unfortunately. So these are 3 formulas that you'll have to add to that big old brain of yours. Just keep working that muscle. Just keep making more, you have more and more things to memorize. All right, let's try another one. The third example is find the derivative of arc cosine of square root of x. So if you look at the formula, arc cosine is negative u prime over the square root of 1 minus u squared. So my u, I'm just going to do a little side work here. My u is the square root of x, but I'm going to write it as x to the 1/2 power. And so what is the derivative of that? 1/2 x to the -1/2. And then I need to make that whole thing negative, because my formula says negative u prime, over the square root of 1 minus u squared. So square root of x squared. All right, so let's do some simplifying here. In my numerator, I'm going to write this as -1 over 2x to the +1/2. I just moved my x to the -1/2 to the bottom of the fraction with the 2 and made it positive. Then on the bottom, I have square root of 1 minus square root of x squared is just plain old x. And I still don't really like that because I have a fraction inside a fraction. So I'm going to keep going. And I'm going to say -1 over 2x to the 1/2 power times what?
1 over 1.
1 over square root of 1 minus x. And then I'm going to say negative times a positive makes the whole thing negative. 1 over 2 times the square root of x times 1 minus x. Now, let me just talk about what I did here on the denominator. X to the 1/2, remember, is just the square root of x. And when you multiply a square root times a square root, you just take the radicand and put the square root over the product. So if I had like the square root of 2 times the square root of 6, or I'm sorry, square root of 2 times square root of 3, that would give me the square root of 6. I only need one square root symbol, and I multiply the two radicands together. Radicand being the expression underneath the square root. So in this case, I had the square root of x times the square root of 1 minus x, so I just wrote it as the square root of x times 1 minus x. I can distribute that x if I want and say x minus x squared, but I don't have to. I can leave it like this if I want. Any questions on derivatives? Yes, sir.
Like since it was like a fraction inside of a fraction, why couldn't you just like flip it and multiply that with the reciprocal of like the bottom?
Here?
Oh, I get it. Never mind. I get it. Because it's like, it's not, it's all, yep, I get it.
You sure?
Yeah, I get it. I didn't realize.
You're good.
Okay.
I got it.
That's all right. Okay, any other questions on derivatives of inverse trig functions? So really, honestly, it's just knowing the formulas and substituting in. The rest is just algebra. Knowing the formula, substituting in, the rest is just algebra. I will say on the homework, I've given you a couple of problems where you have to use these formulas within other formulas that we've learned, like product rule, maybe quotient rule and that sort of thing. So just be aware of that when you're working through your homework problems. But this is the gist of it. New formulas, substitute in the formula, and use your algebra skills. So now let's move on to 5.9, which is taking the antiderivative involving inverse trig functions. So it's still inverse trig functions, but we're dealing with antiderivatives. And so we're going to have 3 formulas. The first formula is going to be 1 over the square root of a squared minus u squared. That gives me arc sine of u over a plus c. We have the antiderivative of 1 over a squared plus u squared. And I should probably go ahead and add a dx on here, because u is in terms of x, just to be proper. We're integrating with respect to x. By the way, a is a constant, u is a function of x, just like it is in all of our formulas. And And then this one's gonna be 1 over A times arc 10 of U over A plus C. And then finally, the last one, which is probably the least popular one, is surprisingly not arc cosine, but it's arc secant. And it looks like 1 over A arc secant of absolute value of U over A plus C. Again, these are not hard problems, it's just so many formulas. So many formulas. Rarely see this one on the AP exam, if ever. So you can probably get away with just arc sine and arc 10. I'm showing you this one on the slim chance that it might show up and you remember it. Okay? But this one is not the slim chance of you remembering it. The slim chance that it will show up. I have confidence that you will remember it. But just the slim chance that it shows up, I'm showing it to you. I haven't seen this one on the AP exam in all the exams I've looked at. But arc sine and arc 10 have been on there. All right, let's do a few problems with this. Anybody still writing? Okay. You good? Okay. So now, if you see a fraction inside an integral symbol, normally what's the first thing you look for? If you see a fraction inside an integral symbol, U prime over U. You check for that first. If it's not U prime over U, then you might have to do long division. If it's not long division, now you look for one of these three forms. If you have a square root on the bottom, or if you have two perfect squares being added, now you have another option to look for if it's a fraction inside the integral. So we'll call this example 4, because we're just continuing really in the same day of notes. So example 4, we're going to take the integral of 1 over the square root of 25 minus x squared. So what I like to do when I'm given these types of problems is I like to first identify what A and U are, and then figure out, is it arc sine, arc tan, or arc secant, just based on how it's set up. So in this case, my A is just going to be not 25, but 5, right? Because this is A squared. A is always a constant, by the way. So it's going to be 5. And U is going to be plain old X. Now, I'm going to just point out here, if U is anything other than plain old X, we got to use U substitution and put this in the form of du. Okay? Most of the time it's plain old X. But occasionally they'll throw in a U value where you have to change it using U substitution. And I'll show you an example like that. But I wanted to mention it to you on our first example here. So A is 5, U is X. Now, is this in the form of arc sine, arc tan, or arc secant? It definitely looks like arc sine, doesn't it? Because there's a square root, so that narrows it down to arc sine or arc secant. And there's not a U out in front of the square root, so it has to be arc sine. So it's just arc sine of U over A plus C. So our answer is arc sine of what over what? 5 over X or X over 5? X over 5 plus C. So again, not a lot of work. Hopefully not that difficult. It's just about knowing the formula and recognizing it and then subbing it. Okay, number 5 is taking the antiderivative of 1 over x times the square root of x squared minus 9 dx. So I start off by identifying my a and my u. So in this case, my a is what? 3, and my u is plain old x. And is this arcsine arctan or arcsecant? Looks like arcsecant, doesn't it? Because of the u out in front of the square root. So my formula for arcsecant is 1 over a, so 1/3 arcsecant of absolute value of u, which is just x, over 3 plus c. Okay, how about this one? How about the antiderivative of 3 over 1 plus 25x squared dx? You know it's the tangent one, right? What is my a value? A is 1. U in this case is 5x. And what did I tell you if u is anything other than plain old x? You got to do u substitution. That's right. So we need to add in, what would my du be? 5 dx, right? So I need to add in a 5 and balance it out with a 1/5 to change it to du. What about this 3 up here? Yeah, it's just a constant, isn't it? Isn't 3 over 1 plus 25x squared the same thing as 3 times 1 over 1 plus 25x squared? So we can just move that 3 all the way out in front of the integral, get it out of our way, and say 3/5 times the integral of 1 over 1 plus u squared du. Now we're ready for our formula. So we say 3/5 times, we said it's arctan, right? So 1 over a is going to be 1 over 1 arctangent of u over a, but what's u? 5x over 1, because 1 is a, plus c. And then if we clean it up a little bit, we'll just write it as 3/5 arctangent of 5x plus c. Just be careful on problems like number 6 because of the u. You have to change it to du to be able to use the formula. That's only if u is anything other than plain old x. Lots of times it's plain old x. But if it's anything other than plain old x, you have to do u substitution. Any questions on antiderivative? The only other thing that I think you might see here is definite integrals. What does that mean? It's got bounds on the integral symbol. Works the same way. You would just make substitutions using fundamental theorem of calculus. Okay, any questions? Derivatives or antiderivatives involving inverse trig functions. Do you agree with me that it's not difficult, it's just the formula issue, that we have so many formulas? If you know the formulas, you can make the substitution, and it's actually pretty easy, I think, as long as you know the formulas. The hard part is just that you have so many other formulas to remember too. So I get that. All right, here's your assignment for these two sections. On page 386, I want you to do 41 through 43 and 45 through 48. And then on page 393, I want you to do 1 through 10. So the first section is obviously derivatives of inverse trig functions, and then the second part is the antiderivatives involving inverse trig functions.